So let's say I have a system like this, okay, and we look at controllability. My question here is, given an LTI system, how do we check controllability? How do we check controllability? So there's a certain test for controllability, okay? There's a test for controllability. And so if you look at these definitions and look what I've just explained, you probably agree that this has something to do with the control U and with the states X. It has really not much to do with measurement here, right? I mean, it's a theoretical thing. We are saying, I mean, in real life, of course, you need measurement, but from a theoretical point of view, we are asking, can I have permissible U's in order to go to X's over here? So I'm looking at what's the control, can I reach that X? I'm not even asking if I measure it or not, right? So this part has nothing to do really with the measurement. It has something to do with the controls and the states, okay? So it really has to do with this part of the LTI. Do I have the controls to reach any X I want in finite time? That's the question I'm trying to answer. Given the U, or is there a permissible U such that I can reach the X, any X I want in finite time? That's the question. So I'm not asking if you have the measurement for it or if you measure the states or any of these things. I'm not asking that. I'm just asking this question, right? So it really has something to do, therefore, with matrices A and B. Okay? Controllability is really related to A and B. So we usually say or ask the question, is the pair AB? Because that's a pair, right? Two matrices A and B. Is the pair A and B controllable? That's the question we are asking. Is the pair A and B controllable? A being the system matrix, B being the control matrix. Is it controllable? Okay? So here is how we have a simple test for that. And I would like to do a few mathematical manipulations, which will also be the proof for the test. But instead of writing the test and then doing the proof, I would like to start from this equation and then do a little math and then reach the test, the condition for this. Okay? So given this, and if you write the solution for this equation, x of t, okay, the solution will look like this. And this is something you probably could remember from your calculus class, or maybe even from system dynamics, I don't know, but it would look like this. This would be the solution, e to the power e, or maybe from differential equations even, b I'm sorry. This would be the solution of this thing, okay? Now this is a differential equation, right? It's x of t. X dot. But if you solve it, solving means that write x as a function of time, right? X as a function of time. So the solution of that would be this equation. So you have the initial condition here, right? And then you have the rest of the solution over here. And this would be xt. Now this is of course not easy to solve because you have a matrix here. What does it mean to have e to the power of a matrix? It's kind of not very easy to comprehend, right? But mathematically this is how it would look like. Now we will do the following. So we want to reach a point xt with permissible use starting from x0, right? That was kind of the idea, right? That's what this definition says. It says, reach any x you want with permissible use starting from x0. Can I do it? So I'm trying to find the condition for this now, all right? So let's say this xt that we are trying to reach is 0, just to make it an easier problem, okay? Just to make it an easier problem. Minus lambda b, sorry, who is this, okay? Let's just say I'm trying to reach 0, just to make the problem easier. I mean, it is like this, right? Let's say this is 0, this is a certain equilibrium point, I don't know what it is, x1, x2, I'm trying to go from here to here. So obviously this point is not equal to 0, but it doesn't have to be. As I mentioned previously, your reference point could be here, then you're going from 0 to this point, or this is, let's say, 5 to 4, I don't know, then you're trying to go from here to here. That x0 over here, go from x0, 0, but this doesn't have to be 0, right? I mean, it really is a reference point. So I'm just saying we are at some other point, but we are going to go to 0, so the 0, 0 point is not necessarily 0, but it's something else. It will just make some of the manipulations a little simpler, okay? So having said this, it means that this 0 could be any point over here as long as you're changing the reference point. So I want to have still a solution to go from any x0 to this with permissible use. So you write x0. Okay, I mean, I reverse the problem a little bit. Instead of saying I know my x0 and I want to go to any xt with any controls, you kind of reverse the problem saying that, okay, I want to go to 0 starting from anywhere. Is there a control? It's kind of the reverse problem, but it's the same idea, right? Instead of going from 0 to any xt, I'm saying, can I go from any x0 to 0? Would be the same idea. Okay, so rewriting x0. So I'm trying to see if I have a solution for x0 given the u now, right? It's kind of the reverse problem. Minus 0 t1 all right, so all I did was take this one to one side, take e to the power at into the integral, so it will remove this at, so you have this one, a minus this interchangeable variable times b u blah blah blah, okay? Question is, do I have permissible controls to reach any x0? Do I have a solution for this? All right? This one here, e to the power minus a, this can be written against something that is coming from calculus, n minus 1. And this is something, this is a relation that we might remember from calculus. E to the power a, this a being a matrix, you could write this. These are constant coefficients. Okay, this is like a series, goes from k0 to n minus 1, where a to the power k. Okay, something we learned from calculus. So if you write this into that equation, you will get this. x0 is minus k equals 0, n minus 1, a to the power k times b, 0 t1, some constants, u this, b this. Okay? So if you look at this, This is a constant. These are the controls that I'm providing, right? And this is a finite integral because it goes from 0 to t1. Okay? So this would eventually become some numbers. And because there are functions of k, and k is part of the series here, right? It's part of the series. Whatever k is, this will be a k. So this will be a series, so it will be some beta k. I mean, it's a constant, it will be a constant number, right? And it will change as a function of k, because alpha is changing with k. U is something that I'm inputting, so, and this is a finite integral, okay? So this will be some finite number if u is not infinity. And u cannot be infinity because u must be permissible control, and u infinity is not a permissible control. So u is a finite number, so is alpha, and so is this integral, and therefore beta k is a finite number, okay? So, in order for x0 to exist, so let's write this down. Open this summation. It will be the first one, k is equal to 0. So it will be, this will be 1, right? A to the power 0 is 1. So you will have b and then this one. So you will have some b. You put it like this. And therefore it will be, k will be 0, so it will be beta 0. That will be the first one, right? This one times this. The second one, k will be 1, and therefore this one will be ab times beta 1, right? So it will be beta 1, okay? The second one will be a squared times b, beta 2. And this would go on until a over n minus 1 times b, and here it would go on until beta n minus 1. Okay? So, the question is, will I have permissible controls u in order to have x0 as any starting point, right? I mean, do I have a solution for x0 with any permissible u's? In other words, given this vector x0 given, is there a solution for this? And the bottleneck in this solution is not this alpha. I mean, this alpha is coming from this definition regarding this a. The bottleneck is, do I have the u's that will satisfy this? So I mean, right? I mean, that's just kind of the definition here. Do I have the u's? Given this, do I have a solution for this? Right? So can I find a solution for this? If I have n number of equations over here and some number of solutions over here, what should be the condition for this thing in order for this solution to exist? It must be? Reversible is not really a good word. You mean invertible. It might not be invertible. Invertible also means something else, because it might not be a square matrix. Invertible means square matrix, right? This is not necessarily invertible. So it should be not diagonal. It should be full rank, right? It should be full rank. If it's full rank, then I have a one-to-one solution over here. You give me this, I always find a solution. So this must be full rank. All right? So the condition then for this to exist is that this matrix is full rank. So if you write this, and it is, if you can write this down, in fact, we can say the system is controllable because this relation exists. So a necessary, you know, invertible versus full rank and determinant not equal to 0. Remember that was for square matrices. That's where we have invertibility instead. I mean, you are going in the right direction. I'm not saying you're wrong. But this doesn't have to be necessarily a square matrix. You will see in a second. Okay? So a necessary and sufficient condition is that for controllability, let's say, we should B, AB, A square B minus 1B is full rank. And this is the test for controllability, what we call the test for controllability. Test for This is the test for controllability. You can also view this in another way. You might say, if it's not full rank, which means one line is the linear combination of the others, that means you don't have a unique solution over here, which means you have a lot of solutions, right? And then if you have a lot of solutions, then it kind of defeats the permissible solution argument over here. Or if you have no solution, actually the problem is not if you have many solutions, the problem is if you have no solution, right? So that would be the full rank thing. So remember that example I gave you where the system was not controllable? What we can do is we can now apply the test and see if we indeed find something uncontrollable over there. Okay? I don't know where to do it. Maybe I can erase this part now. The problem, I think it was example number 2 maybe, 2 or 3, I don't remember. I mean the one that we had, the previous one, was x dot is equal to minus 2, 0, 0, minus 1, 2, 0, u. Remember? That was the equation. And when we said we cannot influence x2 because it's not connected to x1 and u is not affecting x2. Therefore, this is uncontrollable. The x2 is uncontrollable, right? So, if you want to apply this test now, what we say first of all, what is the size of this system? It's 2, right? So therefore, n is equal to 2. That's the size of the system, right? It's a two-dimensional system, not two-dimensional, but a 2 second-order systems, LTI order 2. Okay, n is equal to 2 because you have x1 and x2, you have 2 states, right? x1 and x2, 2 states, and therefore n is equal to 2. So if n is equal to 2, we need to look at this. N is equal to 2, which means AB. So you need to look at A and AB for n is equal to 2. Okay? And we need to check if this is full rank or not. Okay? So, first find AB. First find AB minus 4. Is that right? Yes. And 0, I believe. 0. So, AB is equal to, A is minus 2, 0, 0, minus 1, minus 4, 0. No. Sorry. Nobody's helping me here. This is BAB. You're sleeping? I mean, I'm sleeping, but you guys are. Zero, 2, and -4, 0. Okay? So is this full rank or not? How do I check if this is full rank? It's a square matrix. The easiest way is to, I mean, you can, I mean, if one line is 0, it has to be, right? But you can, I mean, the way you look at this is you look at the determinant. If the determinant is equal to 0, it's not full rank, remember? So, okay, look at the determinant of this. Determinant of this matrix, BAB, is obviously equal to 0, right? So, not full rank, not invertible, and therefore the system is uncontrollable, or we say the controllable is it has uncontrollable states. Not full rank has uncontrollable states. States with uncontrollable states. So is it controllable? It is not. It is not controllable. Okay? These are all equivalent statements. Okay? We would say it is not full rank, it has uncontrollable states, and therefore the system, the LTI, is not controllable. LTI is not controllable. And we knew that already because we made that argument looking at this. But this is quite useful because now, regardless of how complex this AB pair is, you can always check controllability with this simple step here. Yes?
Can we understand which state is uncontrollable looking at this?
No, you can't.
Is there a way?
No, well, there are ways, but for this particular, this test only will tell you, even if there's one point on the system that is uncontrollable, this will become not full rank. It might be one state, the whole state. It might be points, right? But it will just tell you that it's uncontrollable. So there's not really, this test really doesn't tell you which point, which state, and all that. I mean, if you want to, you know, what I'm doing in this class, this is an undergraduate class, right? So I'm trying to explain things in a rather simple manner and try to give you the fundamentals to give you a starting point. If you want to learn more about controllability and all these tests and what else can be done, there's tons of material out there. Lots of papers, lots of books. But once you understand this, you can now go and start reading, okay? I could talk about this for weeks, okay? But then we would not be able to do the other things. I mean, the goal of this class is really to give you the fundamentals for you to start to work on these things by yourself maybe, or continue to working on the areas that you're interested in, and maybe even make you more interested in the subject so that you take other classes where you go deeper in these concepts, okay? I mean, I would love to speak more about this, but there's so much stuff I want to get you a starting point, okay? Understood? Got the idea? Okay. So the next part then is observability. Now that we've gone through this, I think the observability part will be somewhat more easier to explain, since I hope you have a feeling for what we are trying to do here. Okay? Okay, observability. This is 2. Observability. And remember, I already showed you what that was. It was basically that in our measurements, we can't really see one of the states. We have no idea about what's happening to the states because one of the measurements does not really show me any of it. Definition. An LTI system is observable if the initial state x0 can be uniquely deduced from the knowledge u of t y of t An LTI system is observable if the initial state x0 can be uniquely deduced from the knowledge of the input ut and the output y of t for all t between 0 and t greater than 0. So what does it mean? It's actually a very precise definition. It's quite nice. So again, an example of a two-dimensional system. Let's say I have two states, x1 and x2. Okay? So it basically says, if I give you the final state x, and this is x of t, right? That's the x at time t. If I give you that state, I'm here, and I give you the time history of the controls u of t, and if I give you, u of t, and the time history of y of t, basically the measurement, okay? Can you tell me what your initial condition was? If I tell you the u's that took me to this point, and if I tell you the measurements that I have measured throughout this line, can you tell me uniquely your initial condition x of 0? If yes, then the system is observable. If this is true for any x over here. If you can tell me that, then it is uniquely observable. An LTI system is observable if the initial state x0 can be uniquely deduced from the knowledge of the input ut and the output y of t for all t between 0 and t. So I'm not asking, given this, given the time history of ut, given y of t, can you tell me the initial condition? Okay. Now, this also means that you can tell me up to here, because this could be my initial condition here as well, right? So I can tell you, given this ut, given this yt, can you tell me x? I can also tell you, given this u and given this yt, can you tell me this, if this was my initial condition? And given all this, right, you could really tell me all x's along the way. Right? This definition actually doesn't only cover that initial condition, it also covers the whole way, because this must be true for all states and for everything, which means that if this was your initial condition, you should be able to tell me if you give me ut and yt, you should tell me x0. If I give you ut and yt, you should be able to tell me this. So everything you should be able to tell me then. So this definition actually covers the whole way. It actually tells you, given ut and yt, can you estimate x of t? I mean, long story short, I tell you what happened in the last 10 minutes in terms of ut and yt. I give you the time history. Can you estimate x of t? Well, you're right. So that's about that. Of course, if you measure in your measurement, if there is every x in every measurement, then obviously you know everything. But if it's not there in the yt, then if you, in that example I had, remember I had only x1 and not measure x2, and x1 and x2 is not connected, so I have no clue what x2 is doing. So then this would not work. But if x2 and x1 are connected, then you could say, oh, I'm measuring x1, and I know x1 and x2 is connected, so I can estimate x2 given x1 and the controls. So that would be observable. But if there's a state that you don't measure and you have no connection to your measured states, then that state is basically lost, and I don't know what it is doing, so you have no estimation, right? And this kind of gives you a precise definition of observability. Does that make sense? All right. So, just like in controllability, definition, a state x star not equal to 0 is unobservable if the 0 input solution state x star not equal to 0 is unobservable if the 0 input solution y of t with x0 is equal to x star is 0 for all t greater than 0. Now what does that mean? Let me just see if I wrote this correctly. Okay, so it means the following: you are at x star, right? This is a state x star, and you know you started from somewhere. X of 0, right? You know you started from somewhere, and you probably reached x0 one way or the other. Okay, so x star is unobservable if the 0 input solution y of t with x star x0 equals x star is 0 for all t greater than 0. So let me just think about this for a second. This is a bit of a confusing theorem. I need to find you a better explanation for this. I'm going to try to write this a little better. Let me just think for a second, okay? I need to think about this and give you a better solution. I don't like this very much. Please take a note here. And this is not exactly correct. Let me just see. What this really should say is that if I know I'm moving from one place to another and there is no outputs, but I know I'm moving, then that state is unobservable because the measurement doesn't show my movement. So that's what it should say. And I would like to make a better definition next time. I have to think about this and make a better definition, okay? So please leave this for next time, all right? But I would, this is questionable. I'm not sure what exactly I meant over here when I wrote this. So I have to think about this. But the theorem is, of course, an LTI system. I think you got the idea over here, but an LTI system is observable if and only if it has no unobservable states. Okay? I think that's kind of straightforward. Yeah.
But for example, when x is 0, x2 might be unobservable, right?
Sure. This doesn't say, that's why this is confusing. I have to think about this. I think I made a mistake over here. So I want to think about this and give you a precise definition. But here what it says is that you need to go from x2 to x0. It doesn't have to be 0. This can be 0. You can start from 0 here. But we are looking here is for the initial condition from xt. Okay.
In the initial condition, we still don't know the x2, right?
Yeah. We don't know any of it. Okay. So, all right. So, given an LTI system, how do we check observability? How do we check observability? Again, x dot equals ax plus bu, y is equal to c of x, and here we assume d is equal to 0. So here you understand that everything has to do something with x and y. I mean, it doesn't really have anything to do with my controls because we are looking if x is moving, do I have any connection to y? Just like we did in the other part with in the controllability, this is really a question of not of the control, but it's a question of x and y, because given the movement of x, looking at y, can I deduce everything about a? Right? That's the question. So we usually say, is the pair A and C observable? Observable. And this is what we mean by a zero input solution. Zero input solution. So which means u is equal to 0. I think I know what I meant by the definition over there now. Here's what this means. Yeah, it's a bit tricky. Maybe I should write this really better, but here's what it means. Let's say you have a state with x star not equal to 0. It's not equal to 0, which means it's not the equilibrium and you leave it loose and you don't have a control, right? And then the solution y of t for that, right, along is always equal to 0 with x0 being x star. So that can't be, because if x0, x star is not equal to 0, then the initial condition, I mean, if you want to deduce the initial condition, it can't be x star either. So therefore, the inputs, if the yt cannot be equal to 0. If it is equal to 0, which means we cannot measure any of it, and therefore it's an unobservable state. But I think I have to state this better. I mean, I got the idea, but we have to state this better. I will do this for next time, okay? I will try to find a better solution, for a better expression for this, at least. Okay, so this is how we approach this, the observability problem. X of t, given the 0 input solution, is equal to e to the power at times x0, right? Again, like we did previously without control. And we have also shown that e to the power at is equal to 0, n minus 1, alpha k, t a to the power k. All right? And the output will be at x0, right? So given that y is equal to, so let's just plug this one into that equation, and you get n minus 1 alpha k t c a k x0, right? So if you write that, remove this part. So y of t will be equal to alpha 0 t c x of 0. So of 0 plus alpha 2 t c times a squared x divided by 0 0, and this should not be equal to 0. Or let's just say, when is it equal to 0? Let's put a question mark. So let's go step by step. We have x dot equals ax. That is the solution of it, right? X dot is xt is equal to blah, 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 given x0. So I'm rewriting that xat over here, writing it into y. Y is equal to c a t x0. And you take this and plug it into that equation. You have this solution. Y is equal to this, right? And this is x0. And that would be x0, and this is now the solution. Now, the trivial solution for this is that x0 is equal to 0, all x zeros, then y is equal to 0. Okay? But if that's not the case, so if x0 is not equal to 0, then if you have y is equal to 0, it means that the system is unobservable, because then you are measuring things, you are not measuring things, though you should be measuring something. Right? I mean, why would you have y equals 0 if x0 is not equal to 0 in this equation, right? So in order for this to happen, you need linear independence to have a solution other than yt equals 0 and x0 equals 0. And in order for that to happen, A square must be linearly independent. Then y is not equal to 0. And you can see these things over here. You have the C, you have the CA star, So they must be linearly independent to have a solution where you have something else than this one. So in order to have that linear independence, we just write it down here. CA star, and CA n minus 1 should have linear independence, which also means it must be full rank. And if this is full rank, system is, or LTI is observable. Okay? And this is the test for observability. Okay? So I realize I went a little fast on this part, and since we are out of time, I will just try to look at it next week again, okay? And we will do the test for the example. And I have a few more things to say on observability, on the test of observability. So I will continue on this on next week, but I just wanted you to have this in your notes so that you can actually start reading and making giving thoughts on these ideas, okay? I will continue on observability next week. All right?